Hi everyone. So welcome back to the class. Okay, so far over the last couple of classes, we have introduced spatial stochastic models. Okay. Okay, and so we introduced local interaction rules, and then we which had elements of spatial structure, and there were elements of stochasticity in the overall, each of those interaction rules or the update rules. Okay, and then what we learned was a technique, okay, of how to write down the master equation, which then basically becomes mean field approximation. Okay, and the funny thing about this mean field approximation is that although we started with spatial and stochastic structure, this is basically a deterministic approximation. Okay, yet it provides some guide, some sort of baselines for us to sort of say what do we expect in this model. Okay, what do we expect the broad qualitative features from this set of local interaction groups. Okay, so that's how the mean field approximation is very helpful. Okay, now of course mean field up, this actually gives us that as what we call phase diagram or the bifurcation diagrams, right? So basically, which is a plot of steady state of the equilibrium density as a function of some key parameter values. Okay, that's what this mean field approximation makes a predictions on. However, many questions remain, right? You can ask, is the mean field approximation true? What is the true phase diagram? Okay. And what are one can sub questions, what are the critical points or the bifurcation points at which the nature of stable equilibrium changes, right? So you can ask all these questions, if you actually were to sort of consider the full model without any approximation, what are the what are these features? Okay, of course, to address mean field approximation is of course an approximation, and in some simple cases, in fact, the phase diagrams can be constructed entirely mathematically, but in a large number of cases, one can only answer these questions via simulations. Okay. Okay, so inevitably one has to do simulations, and something I hope we will implement both as a part of project as well as a part of, I'll try to provide some codes. I don't know if they will be in R, but I'll try to provide some codes that simulate these models. Okay. Some of the models are of course fairly easy to implement. For example, the binary choice model that I explained is fairly easy to implement. I hope you can implement it on your own. Okay. But the spatial contact process, that's sometimes slightly difficult to implement, especially the one with positive feedback. Okay, so today is the lab time, so I want to make sure you understand this master equation, mean field approximation really well. So these are, with that in mind, if you have no more questions, I will go on to I will go on to describing the lab work today. Okay. So are there any general issues that we need to discuss today before we go to the lab work for today? I understand for the projects, there must be some discussion. Can we quickly discuss any doubts you have? So let me just state what I have already said in the email. I have asked you all to send me information about your group member, what's the project you want to work on. And by Monday or Tuesday, I will tell you if it's acceptable. If not, I will also give you a list where you can pick your project from. By the next weekend, that must be final. However, there are two crucial things I want you to, keep in mind. Groups. I'm not going to accept individual projects. Okay. Now, why is that so? For two reasons. One, how many students are there in this class? 24 who are present today, right? Assuming that this is now the some sort of a stable equilibrium that we have reached, asymptotic equilibrium, no more students drop out. Now, I'm not going to be able to grade 24 projects. It's very, very hard, difficult for me to make reasonable evaluations of 24 projects. So therefore, the groups have to be at least in 2 or 3 members. Okay. In some exceptional cases, I can accept 4 members. Okay, but it should be 2 to 3 members. 3 ideal, 4 exceptional, 2 are okay, but certainly no single group members. If you are still a person with single group, there is just no way I'm going to be able to grade you. Okay, so please find somebody. Now, is there anybody right now who hasn't yet identified a group member? Okay, let me just focus on the crediting students first, because I'm not obligated to grade auditing students, at least the crediting students. I mean, of course, auditing students, you must present. I'm not saying don't present, don't give me a report, but I don't have to formally grade you, right? But, crediting students, I have to formally grade. So I need some kind of, I need to do it rigorously, right? I cannot do it in a sloppy way. So I just want to make sure that every crediting student has by now a group member. Is there anybody who doesn't have Aman, Anand? You don't have a group member? Is that right? Anyone else?
Yes. I don't have.
Who doesn't have? Bevan also doesn't have. Who else doesn't?
Yeah, me either.
Okay, so all of you raise your hands. I'll just know exactly who you are and how many you are. For those who do not yet have a group member. Okay, only 3. Then we have a solution. Okay, 4. But Shrish, you're not a crediting student, so I'm going to ask you to lower your hand. Thank you. Okay, 3. So Aman, Sean, and Bevan, the 3 of you are crediting students. And what about Aman? You just lowered your hand. Why? You're not crediting? Okay.
Yes, I was.
So all of you are crediting, and you haven't found a group member. Now we have a solution for the problem, which is that the 3 of you will automatically become the group. Okay.
All right. Yeah.
Okay. So please discuss among yourselves what do you want to work on. Okay. Now you can lower your hand. Thank you very much. Now, what about the auditing students? Please again, I encourage you to do some project. But I also understand if you cannot do. Okay. But again, for those who are doing, so how many of the auditing students want to do a project? I remember Arshad had sent me an email. Who else? Sambita, Richardson, okay. Arshad, Paras, 4 of you. Okay. Ashrit, 5. Okay, only 4. Okay. Paras, okay, 5 of you. Okay. Now, between you all, can you make 2 groups? Arshad had already sent me one project proposal that seems interesting. I mean, certainly to me. Okay. But it is slightly mathematical and computational. For those of you who are interested in that kind of an angle, write to Arshad and see if you can join that group. But if you want, I don't know, maybe Shambhita and Literasun and I don't know about other, Paras. Do you want to work more on the empirical side? Then you're welcome to sort of, also work on something on those lines and come up with a project together. I think Literasun also has experience with previous theoretical ecology course, and Shambhita has experience with, of course, a lot of research in ecology and thinking about agents in field context. So, so figure it among yourselves and come up with a project. And, send the details to me. I will not formally evaluate, obviously, but I will certainly welcome you to present. Okay. Do you want to say anything? Yeah, go ahead.
Is it okay if an auditing student and a crediting student group together? Vivek and I were thinking of doing something together.
It's well, how is there anybody else, or is there only going to be two of you?
Only the two of us right now.
But the only problem is it effectively is a single crediting student, though.
Yeah.
No? So ideally, that's not what I would like.
Okay.
I mean, okay, why don't you send me an email? We will figure out if there are one more such case. I will try to put you together, some of you together. Okay.
Sure.
Okay. Any other possibilities? Okay. I mean, auditing students, I can be more flexible because anyway, I wanted to formally grade you. But crediting students, I mean, of course, Lakshya, yes, go ahead.
No, sir, it was a general doubt. So maybe you can finish and then I'll ask.
Okay. Crediting students, I mean, the general comment, not specific to Ashrit and Vivek, who I trust will do really good work. But that generally, because auditing students are not at the same sort of expectations as the crediting students, so potentially crediting students might be at risk by, because the expectation of a two group member will be still same as two crediting group members, right? So there is of course a chance that, if you have auditing members, they may drop out midway and therefore the responsibility falls on you to complete the project. Okay. That risk will be there if you are the sort of, sole crediting member in your group. Okay, sounds good. So I will stop here and then about the group formation. Now the next point I want to discuss will be about the topic. Any doubts you may have about the topic? Okay, now Lakshya, what's your question before I get into
I was asking if you could give maybe a sample of a project idea, because I mean, so at least me and my group are sort of struggling to come up with an idea, and we don't know what your expectations out of a project are either. Because so usually in other courses where we have projects, the professors provide us with like the last year's projects or something like that. So we can look at it and decide, that this is the level we are aiming for.
Okay.
So something like that, if that can be done, because like till now, my group at least has not been able to come up with an idea.
I see. I can try to think of what people did in the previous years. For example, I remember a few years ago, one project was basically was a project of evolution, evolution of two alleles, in a spatial stochastic context. So in EC 201, we learned. Did we actually learn? We have done evolution, right? Okay, we have done evolution, right?
Yeah, for two alleles, we did that.
Yeah, we didn't do a Hardy-Weinberg. Did we do Hardy-Weinberg?
No, I don't think so.
But we did the evolutionary game theory, right? Okay. So what they had done was, taken some, extension of some of the standard evolutionary games that we study in EC 201. Like, think of, I don't think this is not exactly what it is, but I'm just giving you an example of the types of the work they did. They took something like a hog-dog game and they implemented it on a spatial grid. Okay, which means the hawks and doves now have a spatial location. Okay, and they have these rules of interaction now, right? Now whatever we learned in the previous course was all mean field, right? When we say a hog-dog game and when you write down the payoff matrix, that's all fine, but the payoff matrix is for any interaction, right? And when you write down the net payoff, we often assume random interactions, right? That means a mean field interaction. Okay. Now, of course, when they are spread in space, that's not necessarily the case, right? Because there is going to be some kind of clustering, when and there will be also birth and death process that happens, right? A new hawk is born, new dog is born, right? So what they had done was they had implemented a spatial evolutionary game. Okay. I think in the context, and of course, what they had done was in the context of speciation. They were trying to simulate the idea of allopatric and sympatric speciation. You may have heard of these words, right? Where there is a physical barrier that causes speciation, and in the other there is no physical barrier. Then you still have a speciation, right? So they were trying to see if such a behavior can be explained in a spatially explicit model. Okay, so that's one example of a project. That's one thing I quickly remember. The other one, for example, the other group had taken, so there is something called a move bank database, okay, where you have the data of lots of animal movements. What they had done was they had downloaded the openly available animal trajectory data and animal movement data, and they had tried to compute very rigorously what are the, for example, the exponents of random walks. Okay, they had tried to compute various properties of the movement. For example, whatever we had discussed in the theory, right? For example, the Levy index. What is the turn angle distribution? What's the jump length distribution? And what is the property of mean square displacement? And also correlations in the movement. Okay, so they had computed these kind of properties. So that's for example, an example of a data-driven project. You take data and you compute various properties in data. The other one is purely theoretical driven project. Yeah, so one can sort of think of these kind of projects. So it doesn't have to be so I mean I would like that you think through it and come up on your own, but as long as it is not an obvious idea that's, let's say, present in some paper, I'm going to be okay with it. Okay, but it's always, I mean, because you don't know the field very well, and you have little time, it's entirely possible that what you do has already been done, and it's quite likely actually, so it's totally fine. But think on your own. That's the main idea while coming up with a project. Any other doubt? Does it give some nice? Is it clear?
Yeah, it does help. It does help.
Okay. Any other? Or usually, how do you come up with a project? Sometimes what you do is you start reading a paper. For example, I have suggested a few papers to read, right? For example, I had suggested this paper to be read, for the second next assignment is due on Monday. Read this paper by Reed Kirk et al. In American Naturalist. So read the paper, you understand it well, and you realize, if I add this new term that captures the processes better, okay. Now, how does that change my results? Now, how does that would be, an interesting exploratory project, okay. Or it could be another model that we have studied in the class of that time. So one can think of many more ideas like that. Another idea could be we have done random walk model in the context of foraging, right? Now when we say foraging in the landscape, were they really foraging targets that but we never really bothered about that, right? So think of take a model, think of the real world, you will see there is a gap. This is a very general way of coming up with ideas in theory, by the way. So look at any classic model and think of the corresponding real world it's trying to model. And then we will see, and then think of all the approximation it makes. So make a list of all the approximations and see which of the approximations do you want to explore a bit further by incorporating that feature now. For example, if you were to think of broadly, even between the previous course and this course, we have relaxed two broad assumptions, right? That of stochastic and spatial, okay? But we're still looking at the same framework of how populations change over time. Okay, so one can, that's one simple way to come up with simple theoretical ideas, simple theory projects. Okay, on the other hand, you can also do data-driven projects. There's absolutely no problem. Okay, and let's say if your area is if you are interested in, let's say, biofilms, right? So there are lots of models of spatially explicit models of biofilms. Read about them and see if you want to make a new model of, explore a given model of biofilms, but maybe it's a slightly newer context that you can think of. Or maybe there is a model of biofilm formation that's too complex. Maybe you want to simplify it. Okay, maybe it's too simple. You want to make it slightly more complex and understand it. But be very clear what the objective is. What exactly are you adding a new component to the existing literature? Okay. So there are some sort of broad ways to think about it. Anything else? Any other questions on the topics? Okay, fine. So somebody had sent some email about some neuro evolution. Can you just ask me what is that question? Or do you still want to ask the question, or?
So, excuse me, sir.
Yeah, go ahead.
Yes, sir.
Yeah.
No, not about that. So regarding that, sir, we know something about like simplifying the traveling salesman problem with like and colony optimization. Like, is it fine if we do something on those lines?
Traveling salesman problem along with what? Sorry.
And colony optimization, like how ants actually like how ants forage, and like based on that they modify the mod, something like that. So like, is it fine if we do something based on these lines?
There are lots of work in the direction. No, just have to tell what is the thing that you will read, what's the thing that you will do. As long as you say it, it's fine. Okay.
All right.
Make sure it has some element of space or at least one of the two, space and stochasticity, because that's the focus of the course. No, it doesn't need to have both. If at least one is there, that will be great. Okay.
All right.
Okay.
So I had another question. So we were thinking of having something which is well studied in ecology in some ways, that the sort of interaction of two populations, but it has not been studied very well in the context of cancer. So like their cells interacting with each other and cooperating with each other. So it is supposed to have both spatial and stochastic components in the model, but like things like those have been sort of studied in ecology. So will it be fine if we study a different system altogether? Need not be, I mean, it will not be directly related to ecology that way. Is that
no, that's absolutely fine. Absolutely fine.
Okay, thanks.
Yeah. I mean, biofilm was one example. Cancer cells could be another example. Absolutely, yes.
Okay. Also, let's sort of follow up. So, is it do we have to build our own codes from scratch, or is it fine if we use some? I mean, like semi-partial, as in some softwares which have coding, but we don't write things from scratch, basically, like say Physicell or Compusel or those kind of things.
That's fine. So you basically will use some existing computational tools, right?
Yes.
That's fine. Yeah.
Okay.
No problem. Yeah.
Thanks.
And make it very clear what's the existing thing that you're using, what's the thing that you are doing on your own.
Absolutely.
State that very clearly, and state the only problem I often see is that when students present, the problem statement is not very well defined, not very clear. It appears very muddled. That's the only thing I will caution you against when you tell me what exactly is the problem that you're trying to address from the system. Okay. And then how are you approaching it? How are you solving it? You have to say these two things very clearly. Don't use too much jargon or too much unnecessary stuff that will hide these two important parts.
Right. I get it. Okay. Yeah, so I mean, once we send the write-up to you today or tomorrow, then we can get input on that, right?
Yeah. So I'll create a form, Google form. That way, you will send me both. Only one team member needs to fill that out. Okay.
Yeah.
Fill that up by at least the group member part by tomorrow. That way, I know that everybody has form group, and then the project description you can do by. Ideally, again, I had told 25th as a deadline. No. Yeah. So by Monday, at least, I just need one paragraph, one or two. Monday, Tuesday is also fine. Okay, because if you're unable to come up with an idea, or if you want my help, then I can then provide a list for you to pick up from. Okay.
Right. Thanks.
Okay. Sounds good. So now, let's go to the work for today. Okay, this is what I thought you could do today, just to sort of strengthen your understanding a bit further. Let me just give you, before I go further, let me just tell you one thing broadly. What shall we do next, right? So far, what have we done? I have we spatial stochastic is how real biological world is, right? Spatial stochastic, right? And also, in a sense, discreteness is very important. For example, individuals are discrete. So spatial stochastic discrete is how the real world is. So we now have 2-3 concrete examples of these type of models. The contact process is one I have described. Even the binary choice model is one such model. So what have we learned is we know how to do mean field approximations for these models, right? That look like this, some state variable X. And we also know the reaction diffusion approximation, right? Under the assumption that the movement is random. So we get now things like this. Okay, now what you are seeing here is in both of them, both of these approximation, what we have not done is there is no stochastic approximation. Okay, so in the next part of the course, I will deal with stochastic part. Now, how will that look like? So to do that again, the full system must have both space and stochastic. So in the first stage, to make life easy, I will deal only with equations of this form, where the space is ignored, but only stochastic part is considered. Okay, and finally, we will a point where we will actually not reach is an approximation that involves spatial and stochastic. There is a very simple reason, because that's this, right? We anyway have the full model direct simulations, right? So direct simulations anyway do that. It actually has all the features, which has spatial, stochastic, and discrete nature of biological entities, right? So we will not do any approximations to capture all of this. There are, but they can become increasingly more mathematical and difficult. So in some sense, mathematically, you have learned 3 different approaches to solve these systems and learned various properties in the process. So this is the next thing that we will be learning over the few weeks. Okay, just to give you a broader picture of where we are right now. And once we have done, so now for this, I have now given you some empirical examples, right? Okay, I hope I have given some empirical examples for this, pattern formations and so on. Here also, I will give some empirical examples. Okay. Of course, this is really more of a technique. So it's hard to think of an example per se for this. Is really more of a technique that's going to be useful here as well as here. Okay. So what I will do is mathematical methods for this as well as some empirical examples for this. Okay. So this is the way broadly I will cover. And once this topic is covered, I will see. Of course, you should also learn the direct simulations of this. Okay, and I will share you some codes. There are methods for direct simulations of this called Gillespie algorithms. Okay, and also Monte Carlo simulations. I will give you some codes and cover the basic ideas behind them. Okay, so that would then cover all the sort of methods that you need to know if you have your own problem. How do you sort of build a model, and how do you go about analyzing the model? Okay. Okay, that's where we will stop this course. That's how the course will progress. So now coming to today, so I thought maybe we can do the following today. Okay, so far I have covered spatial stochastic model in 2-3 contexts, right? Now we all know predator-prey systems, right? So here I have 2 questions for you. Question 1. Write a stochastic spatial model for predator, prey systems. Okay, so you have the liberty to sort of write your equations. That's the first thing you will do today. And the second thing you will do is write mean field approximation. For this, is that clear? So you will write your own model and you will write your own mean field approximation. Each group will do this. Okay, that's your task for today. Any questions on this? Any doubts? So what you do is, again, always use the principle of parsimony, write the simplest possible model. Okay, maybe I would recommend if you have time, if you do write the, step 1 for both of them, write the simplest possible model. Okay. And then do 1 and 2. And I also want a specific question. I have a specific question about 2. How does your mean field approximation relate to Lotka-Volterra predator-prey model? Okay, and then the next thing I want you to think of is a next, maybe more complex model. Again, there are many ways. So just take one step. Don't add million rules. Just add the simplest possible rule, addition in addition, and repeat the step 1 and 2. Okay. So this step 3 only if we have time. Okay. So today I would like you to submit by 4:30. So do the submission by 4:30. No need to go back home and do it. Okay. I'm not asking you to solve the equations, by the way. I'm just asking you to write the equation. Write the model, write the equation. Okay. Okay. Any questions on this? Okay, so please start. I will start the, can I unshare this?